An AI developed by Google just discovered over 2.2 million new materials. In this video, we'll delve into the fascinating world of material science, where the boundaries of technological innovations are being pushed by the introduction of Google's latest AI-powered tool, GNoME. Join us as we explore this incredible technology and its potential to revolutionize material research and future technologies. From electric vehicle batteries to solar cells and microchips, revolutionary advancements in technology often rely on the discovery of new materials. However, this discovery process has historically been time-consuming, taking months or even years of trial and error research. But what if there was a way to accelerate this process? This is where Google's breakthrough with its new AI module comes in. Google's Graphical Networks for Material Exploration, or GNoME for short, is DeepMind's latest AI-powered tool. GNoME utilizes deep learning to drastically expedite the process of discovering new materials. In a groundbreaking study published in Nature, GNoME is shown to have successfully predicted structures for an astonishing 2.2 million new materials. But what exactly is GNoME? It's a tool specifically designed for the discovery of new materials through the use of deep learning, a form of artificial intelligence. By analyzing the chemical makeup of various materials, GNoME is capable of determining their structures and characteristics. This is of utmost importance because materials play a crucial role in our everyday lives, from solar panels and batteries to the chips in our computers. Through the discovery of new materials, we can potentially find alternatives that are better, cheaper, and more eco-friendly, addressing significant issues like energy storage. To understand this, I would like you to imagine a world without the materials we have right now. Imagine we did not have cotton, wool, linen, and many fabrics we use in making clothes. Imagine we did not have plastic. While plastic has been a great concern for pollution, we must not forget that it has been used in a lot of useful inventions, including those used in hospitals to save lives. Simply put, a technologically advanced world without the millions of materials we have created would have been impossible. What GNoME has done is revolutionize the field of material discovery by exponentially increasing the number of technologically viable materials. Out of its impressive predictions, 380,000 show promise in terms of stability, making them strong candidates for experimental synthesis. These materials have the potential to power supercomputers, develop superconductors, and boost the efficiency of electric vehicles. This achievement showcases the remarkable potential of AI in the discovery and development of new materials on a large scale. Let me tell you how GNoME does that. Traditionally, the process of finding new materials has been pretty difficult and time-consuming. Scientists spend years experimenting with different elements trying to find the perfect combination that shows the desired properties. Even when a successful material is found, understanding its underlying structure and improving upon it can be a challenge. But note that we have a wealth of knowledge about the materials we have created so far, and this knowledge can be used to make a lot more materials. The problem is that we as humans are slow, and we are not efficient either. But with AI, we can quickly look through all the knowledge we already have and see what bits we're missing. This is where GNoME becomes a game changer. By leveraging existing information on materials, GNoME can predict new ones with incredible efficiency. It can also analyze millions of materials in just a few hours, a task that would normally take years. The results achieved by GNoME have been nothing short of extraordinary. Remember those 2.2 million new materials for which GNoME successfully predicted their structures? That is nearly 800 years of scientific knowledge that was achieved by GNoME in a few hours. To further validate these predictions, over 700 of those new materials were synthesized and tested in the lab using a robotic system. The results were staggering, with GNoME's predictions proving to be accurate in over 90% of cases. To understand how GNoME works, we will need to look at the module involved. The GNoME module has two main models. The first model, which is called GNoME Stability, assesses the likelihood of a material being stable based on its composition. Using a graph neural network, GNoME represents materials as a network of atoms connected by bonds, allowing it to process and analyze the data effectively. The second model, called GNoME Decomposition, calculates the energy required to break down a material. By considering the material's composition and stability, GNoME determines the energy needed for separation. This model employs a transformer network ideal for analyzing sequential data. Now let us look at some of the amazing materials it has been able to discover. Over 700 of the materials discovered by Google GNoME are already in labs undergoing testing. One of these materials is copper zinc tin sulfide, CZTS. which has been proven to be an excellent choice for thin-film solar cells. It is not only cheaper and more flexible than traditional options, but it also excels at efficiently converting sunlight into electricity. Lab tests confirm GNoME's predictions regarding its stability and low breakdown risk. Another notable material is lithium iron phosphate, LFP, which is ideal for lithium-ion battery cathodes used in electric vehicles and electronic devices. LFP is known for its energy efficiency and durability. Once again, GNoME accurately predicted its stability, a finding confirmed through extensive lab tests. Zinc tin nitride, ZTN, is another significant discovery. It has the potential to revolutionize transistor manufacturing for computer chips, offering fast and efficient electrical conductivity. GNoME's predictions regarding its structural stability and low decomposition were also validated in the lab. Let's talk about some science. After all, without chemistry, we cannot synthesize materials. I know this is going to be a bit technical, but stay with me. The process of discovering new materials involves combining elements across the periodic table. However, due to the vast number of possible combinations, traditional methods are often inefficient and slow. Scientists have typically relied on modifying existing structures, but this process is time-consuming and limits the potential for unexpected breakthroughs. DeepMind confronts these limitations by adopting a unique dual model approach. The first model generates over 1 billion structures by modifying existing materials, while the second model predicts the stability of new materials solely based on chemical formulas. By combining these two models, GNoME allows for a broader range of possibilities, speeding up the discovery process. Once candidate structures are generated, GNoME employs advanced filtering mechanisms. The models predict the decomposition energy of each structure, a crucial indicator of its stability. The most promising candidates are selected and evaluated using established theoretical frameworks. GNoME's success stems from harnessing the power of graph networks and utilizing two pipelines for material discovery. The structural pipeline creates candidates based on known crystal structures, while the compositional pipeline employs a more randomized approach focusing on chemical formulas. These outputs are then evaluated using density functional theory calculations, a technique used in physics, chemistry, and material science to assess the stability of crystals. Through training cycles and active learning techniques, GNoME's performance improved significantly, making it a game-changer in material stability predictions. One thing you need to know is that while it has produced impressive results, GNoME is utilizing an iterative learning process. In the ever-evolving landscape of artificial intelligence, the mantra seems to be fail fast, learn faster. This mirrors a dynamic dance of progress and setbacks. AI doesn't follow a straight path to success. It's more like a winding road with unexpected turns, potholes, and detours. This is not a system that magically solves all our material production problems. It has to learn and relearn just like us. Machines encounter unexpected scenarios just as we do in our lives. They adapt, modify, and rewrite their operational scripts, a parallel process that echoes our capacity to embrace change and rewrite our narratives. You might be wondering how they do that. Here's how. GNoME, much like humans, learns from failure through a process of analysis and adjustment. When algorithms stumble upon an error, they analyze what went wrong, tweak their approach, and try again. It's a continuous cycle of learning and growing. While GNoME lacks human emotions, its growth can be seen in its enhanced performance and problem-solving abilities. This learning manifests in the form of improved algorithms, increased efficiency, and refined decision-making. GNoME and its continuous learning reflects our very essence. It mirrors our capacity for growth, adaptation, and the indomitable spirit that propels us forward despite adversity. In its initial stages, it boasted a 5% precision rate in predicting materials stability. However, through subsequent training rounds, GNoME successfully predicted structure stability over 80% of the time for the first mode. This significant improvement showcases the power of AI models to uncover new materials. Is Google the only one making strides in this area? While GNoME's application in material discovery is not entirely novel, its size and precision set it apart from previous endeavors. The Materials Project, led by Kristen Person at Berkeley Lab, has utilized similar techniques to discover and improve the stability of 48,000 materials. Nonetheless, GNoME possesses a more extensive training dataset which enhances its efficacy. In addition to GNoME, the Lawrence Berkeley National Laboratory has announced the development of an autonomous lab. This state-of-the-art facility combines GNoME's discoveries with machine learning and robotic arms to engineer new materials without human intervention. Professor Ju Lee of the Massachusetts Institute of Technology draws a parallel between GNoME and AlphaFold, another AI system developed by DeepMind. While AlphaFold revolutionized biological research and drug discovery through the accurate prediction of protein structures, GNoME aims to do the same for material discovery. As a result, the number of stable materials known to humanity has increased almost tenfold since the deployment of GNoME. Before the introduction of GNoME, similar calculations were expensive and limited in scale. However, GNoME allows for computations with higher accuracy and reduced costs, facilitating the scaling of these operations. The impact of these advancements can be enormous, as they accelerate hardware innovation across industries such as energy, computing, and more. Through external validation, 736 of GNoME's new materials have been successfully synthesized in labs worldwide, proving the accuracy of the model's predictions. By releasing the database of newly discovered crystals to the research community, scientists now have access to a comprehensive catalog of potential recipes for new candidate materials. This resource will undoubtedly facilitate testing and potentially lead to the creation of some of the most promising materials. So watch out, someday you're going to be using something wonderful that GNoME produced. You may want to check out our other videos for more amazing technological advancements in AI, and don't forget to hit that subscribe button.